Today, you accept and have lasers, various kinds, various power levels.
You know, one of the reasons that I find the laser industry so fascinating is because the problems that we're working on are truly global problems and truly, you know, global opportunities.
It's probably as important to the modern age as, you know, electricity was back in Edison's day, or the radio was in, you know, to the communications industry.
You can't really practice dermatology or ophthalmology now without access to laser.
The laser will push the boundaries of what's possible in the manufacturing world.
I would say that the discovery of the laser has been absolutely pivotal to the success of photodynamic therapy.
Lasers have a very important role to play, and I think we can utilize it even more.
Clearly the laser has had significant practical impact. I mean, from CD players to telecommunications to the cheapness of high-speed communications, the fact that that's enabled that, and that's all made possible by lasers.
You know, every time I go into a store and notice the laser scanner that reads the barcode, you know, it just for a small instant, you know, takes me back to, you know, before that. And it's just amazing to me that some of the uses of lasers have become so commonplace we don't even realize they're lasers anymore.
I'm sure to an extent this is taken for granted, and at one time there was some question about whether a laser could indeed be made.
On May 16, 1960, at Hughes Research Labs in Malibu, California, the laser was born. Engineer Ted Maiman had figured out the right architecture involving a pulsed xenon flash lamp and a ruby rod to generate coherent light. While this event began a new age of technology which now permeates our everyday lives, exciting developments both before and since are all part of the fascinating story of the laser. In 1916, Einstein had predicted that rays of light could stimulate atoms to emit more rays of the same wavelength. By the 1950s, several researchers were working on theories that led to the laser. The maser, which amplified microwaves, was pursued throughout the decade by Charles Townes at Columbia University. Townes had a maser working in 1954. Parallel work was underway in the Soviet Union by Alexander Prokhorov and Nikolai Bazov, who built one in 1955. The work of these three would earn them the Nobel Prize in Physics, the first of 14 Nobel Prizes related to lasers.
We called it a maser for microwave amplification by stimulated emission radiation. A lot of people worked in the field. Most people didn't think they'd get to shorter wavelengths, but after 2 or 3 years of masers being all exciting to everybody, I decided, no, I want to see how to get right on down into the shorter wavelengths, which is what I really wanted. So I sat down again and thought about it. Oh, hey, it looks like we're getting right on down to optical wavelengths. Oh boy, and so Arthur Shallow and I wrote a paper on how to get down to optical wavelengths, and that was the origin of the laser then. But the maser idea was the basic idea.
In addition to all of the rumblings and stirrings about let's make a laser, let's make coherent radiation in the infrared or optical part of the spectrum, there were some scientists who were coming up with ideas and arguments on why this was either fundamentally impossible, respected scientists, so it was not to be ignored, or practically impossible. The momentum built up, and the race, the excitement.
Once the maser was invented, yes, there was a lot of competition in that field, and this is why when Art Shallow and I published a paper on the laser, we were careful not to say anything about it until we wrote a theoretical paper, because we knew if we started to work on it, people would know that, and then everybody would jump in the field and would have competition. So we write a theoretical paper saying it could be done.
The power of that competitive race, we were getting rumors every day that somebody else either really had a laser and just hadn't announced it yet or was about to have one.
All the first lasers were built in industry, and I tried to build one, but they beat me to it. Ted Maiman, of course, made the first laser work.
This is really it. This is the laser. And here's the polished cylinder. and a flash lamp and a ruby, mirrors on either side. The news release hit, pandemonium broke out. Just all hell broke out. For one thing, a number of scientists weren't sure that this was for real. And so there was some controversy, and one of the trade publications, I think it was Electronic Design, had a headline. They had to cover themselves. They didn't want to not cover it, and they weren't sure, so they had a headline that said, if he has what he thinks he has a laser. And I got off the podium, and a whole bunch of reporters gathered around me, and this was my first experience with the media. And the man asked me, and he said, "Gee, I hear that this device is going to be a military weapon." And I said, "Gee, I didn't see anything in our news release that talked about anything like that." And he says, "Well, but I hear it is it?" And I said, "No, it's, I don't know, I guess conceivable, or no, I didn't even say that. I said the practicality of that is not high on the list. I see other things that we've talked about." Well, he pressed, and he put the question a different way, and finally he got me. He says, "Dr. Maiman, are you willing to say that this couldn't be used as a weapon?" And I said, "No." He says, "That's all I wanted to know." The headline said, "LA man discovers science fiction death ray." That was, that was the headline.
50 years after those infamous death ray predictions, we have yet to see a laser used on a battlefield as a direct weapon. What the laser has provided us is a new tool to help secure the safety of civilians and soldiers alike, as well as an important piece of much of the advanced equipment found in conflicts today. From range finding and weapon detection to advanced missile shields, the laser has and continues to play a large role in defense and security technology.
The most immediate application is for laser spectroscopy for detecting chemical and biological sensing of one kind and another, things like greenhouse gases or chemical and biological threats or explosive detection. And for that application, our lasers are pretty close to being where they need to be already, and we've been getting increasing number of inquiries about people wanting to use our lasers.
We have had considerable success in using laser-based techniques for the detection of both explosives and chemical warfare agents. One of the important part of our chemical warfare agent detection is that we not only have high sensitivity, but very good selectivity. What do I mean by selectivity? By selectivity, we mean how many false alarms you will get. False alarm is a very important issue because if, for example, a chemical warfare agent were to be deployed in a building, large building, and the alarm goes off, what option do you have? You have to evacuate the building. You cannot stand and ask around, was this a false alarm, was this real or not? And so having very low false alarm rate is very important. In the area of the optical detection of either a particular target, whether it's a chemical warfare agent or ammonia or something like that, what you want to do is to make sure that the particular absorption wavelength that you are using for corresponding to the target is not also absorbed simultaneously by something else that is present. If something else that is present, that something else will give you a false alarm. Now you get around this problem by making sure that you tune your laser over sufficiently wide spectral region so that you not only measure your target, but you also measure other things which could possibly interfere.
The Navy's biggest drivers for infrared countermeasures to defeat heat-seeking missiles that with the right laser of enough intensity, you can jam the missile into going off course. You don't have to damage it, you can just confuse it. You need a lot of power for that. The quantum cascade lasers are starting to get to the powers you'd need. For the interband cascade, they're somewhat longer wavelengths. For the interband cascade, we need to still work farther on the power. We're still not where we need to be, but we are making progress in that direction, and that's what the Navy's most interested in.
And so I think as we move forward, as these kind of the defensive devices get widely deployed on military planes, eventually they'll become inexpensive enough to be also deployed on civilian aircraft, which will make civilian aircraft a lot safer.
It's true that most of the first headlines focused on the laser's potential military uses, and a lot of the early developments came from military research. But from those early studies came many other applications, some foreseen and others not. One of the earliest of these was the use of lasers in medicine.
A lot of us were very skeptical about the high-energy lasers ever being really, a lot of us who worked on Star Wars, I don't want to speak for everybody, we're skeptical from the beginning about the Star Wars program and high-energy lasers. But we loved to do the work, and a lot of the money was used, as I say, in my program ended up to be applications other than Star Wars. I had cardiologists, dermatologists, orthopedic people, ophthalmologists. These were MDs and residents at NIH come over to my lab to use some of the lasers that we had developed and had in our laboratory. So it was interesting because I certainly learned a lot from them, and they learned a lot about the utility of these lasers. It turned out that they felt that some of these would have some medical applications.
Almost immediately after the laser was developed, doctors and surgeons alike were excited to find ways to introduce this new tool into their field. Today, lasers are playing a big part in our ability to diagnose and treat disease, as well as improve the quality of life for many through cosmetic means.
The idea of using lasers diagnostically really started in the laboratory, where people said, well, can we look at biological specimens with fewer reagents? Can we count blood cells, for example? The early uses of lasers was in counting blood cells, still being used today for blood cell counting. The first foray kind of into diagnostic use of the laser, in my opinion, was in the laboratory, and later the thinking turned toward taking these laboratory procedures, pulling them into the clinical domain so that people can use them in real time, in vivo, on patients.
Ophthalmologists were the first people to introduce lasers in medicine, so we were early on the scene actually. As soon as ruby laser was discovered, it was introduced into medicine, and I have always in my talks started out from the different laser wavelengths because they act so differently in tissue. So for medical people, in many specialties, lasers is extremely important.
Early 1980s, we began to work with pulsed dye, tunable organic dye lasers, and configure them to go to wavelengths that would interact with blood in your body. And out of that came the first surgical lasers for treating babies with these vascular birthmarks you see, like Gorbachev had on his forehead. We can now remove those from kids when they're newborn.
So photodynamic therapy happens to be a treatment modality now. It's a photochemistry-based modality where the basic idea is to take a chemical and excite it with light. And the most efficient and traditionally the light source that's been used for this has been a laser with a wavelength specific excitation leads to the energization of these chemicals, which then can result in killing cells around which this excitation has happened. And so traditionally the focus has been on using photodynamic therapy for the treatment of cancer. And here the invention of lasers has actually been a terrific boom because the first phenomenon in photodynamic therapy was really discovered 100 years ago, where it was basically sunlight and a chemical getting activated. But right now, lasers such as this are used in the treatment of lung cancer, where you can take this fiber here and thread it through a bronchoscope and go inside the lung through the bronchoscope. It's being used routinely for the removal of obstruction in esophageal cancer, where patients basically could not eat or swallow or drink anything. And in fact, what this does is that it removes that obstruction.
The laser offered an opportunity for another field, the field of communications, to actually meld with what we were trying to do. A lot of the mathematical techniques in communication theory and signal processing has been able to be applied with this wonderful source of light, the laser, to give us optical coherence tomography, interferometry that we never had before. And these have led to really novel approaches that we're only yet beginning to apply in medicine and biology. There's a great future ahead.
Well, the interesting thing about OCT is that it's a very general technology. Essentially, it's a way that you can measure both cross-sectional images as well as three-dimensional structures inside both materials and biological specimens. So it has quite a wide range of applications, going from fundamental science to clinical applications. The dominant application is in ophthalmology, and it's now a standard of care. So I think that if you go into pretty much any ophthalmologist, especially the specialist ophthalmologist, glaucoma or retinal specialists, the OCT diagnostics are now a standard. And if we look at other areas, one of the big areas that's emerging now is intravascular imaging, that is fiber optic imaging of the coronary arteries. And one of the interesting things about cardiovascular medicine is that you can use OCT to assess so-called unstable plaques, which are prone to rupture and cause myocardial infarction or heart attack. You can also use it to assess the placement of stents. Stents are wireframe devices that are inserted into the coronary arteries to treat blockages. So this is an emerging application of OCT. I think we'll start to see these applications coming to the clinic in the future.
I think if you look very broadly at the impact that laser and optical technology really could have in health, you know, cancer, you look at the major diseases, heart disease and cancer have got to be number 1 and 2. And we are actually making a lot of progress there. I'm very excited about the optical coherence tomography as a imaging tool for looking at heart vessels, coronary vessels.
If you look at most of the applications in medical lasers, they're really based on some relatively old laser technology. And so now that the researchers have some new technology and are seeing what you can do, they're really catching up, although I think things are improving so rapidly in lasers that there's still a lot of opportunity there. And I think medical applications will be one of the most interesting applications in lasers. And certainly one of the most rewarding areas too.
Perhaps one of the most influential uses of laser technology today is in material processing and manufacturing, where the laser's ability to cut, mark, etch, and align with accuracy is unmatched.
In material processing applications, I think those are maybe less accessible for people, but they're equally profound. So whether a car part is being welded or cut, or new applications in the solar industry, lasers have been used across a wide range of different industries. And while those may not be quite as glamorous or as accessible, I guess, as medical applications, they're profound, and they are changing how things are built and enabling new technologies that we all use.
In the mid-70s, when the laser CO2 lasers became more powerful, it was shown that it is possible to do contour cutting in sheet metal with lasers. And of course, that was very interesting for Trump, because at that time Trump was considered the premier company in the world for making nibbling machines for contour cutting sheet metal with this consecutive punching method. And therefore the laser was, if you will, a disruptive technology. So we had to look into this new tool, which was then done in 1978 when my father traveled the United States, which was at that time the only country where lasers of that type and power were manufactured, to look at different laser companies. He ended up buying a laser system from a company that had originated from the defense industry, which probably was the case for most high-power laser companies at that time, which we then married with a punch press and we actually managed to then develop the laser cutting process on that punch press, which at that time, very interesting, it was necessary for laser cutting of sheet metal to do it on a punching machine, because you could not pierce the metal with the laser. You would have to start the laser beam in a punched hole and then start moving the sheet, and then the cutting process would start. And there were a lot of talks giving at conferences and papers published that proved that this would never change, that you would always need to be able to punch a hole first and then to start the laser cutting process, which of course was wrong. Today, the majority of the laser cutting machines are laser-only machines.
And so that is having a major impact on cost reductions for our TVs, our cell phones, for drilling holes in PC boards. As the cost of our miniature electronic devices, whether it's a laptop or cell phone or what have you.
One of the most common applications for lasers these days is the laser marking of different materials. And different types of lasers can be used to mark different types of materials, from metals to plastic to glasses. And while many people don't really realize it, a lot of us come into contact with parts marked or manufactured by laser in our everyday lives. As soon as you select a radio station on your car radio, you're touching a button that was laser marked with a part. If you put on makeup in the morning, when you figured out what kind of makeup you put on, it's usually marked with a laser on the tubes, as well as medical applications where we identify the different kinds of parts which are placed in medical applications and sometimes inside the body to help us lead better lives.
They really want lower cost and higher volume, and so the laser seems to be attracting those. And as a matter of fact, that seems to be the trend throughout a lot of the industrial areas where low-cost miniaturization is becoming more important. Lasers are becoming more and more useful as machine tools in the material process industry, in the engraving industry. And they process glass and ceramics, metal, plastics, wood.
The heavily curved wing sections where they go, where they meet the fuselage, basically, under the surface of the wing, are being formed in shape and stress compressed by thousands of laser pulses from these average power solid-state lasers today. So that when you get on, one of these big aircraft with these Rolls-Royce engines, it's the average power solid-state laser technology we developed at Livermore that's holding those turbine blades together for you.
The use of lasers in factories and plants around the world is growing, and it's almost impossible to go a day without coming into contact with a product touched by a laser. Also, our ability to communicate with friends or colleagues around the world is enabled by lasers. The fiber optic networks that run our digital lifestyle, from email to YouTube, are made possible with laser light. The laser's ability to send pulses of light over very long distances makes our world smaller through the increasing speed and bandwidth of the internet.
If I was to pick a laser that had the most impact on society, it'd probably be the semiconductor lasers. The semiconductor laser has revolutionized entertainment, our video disc, data storage, telecommunications. Even though we had a bubble that burst not too long ago, in such a short time to have the world completely communicating by fibers underseas and for telecommunication is just amazing when it happened, and it happened so quick.
There's enough fiber installed today to span the world on the circumference 23,000 times. It's being put in at 1 million kilometers a year at the moment. So there's vast factories churning this stuff out, all enabled, when you think about going back to the history, by first of all the Charles Cowell work, and the Corning work, and then the optical amplifier. And interesting question is, what's next? Because, we are running out of this bandwidth. And you look at the projections, the data rate in the fiber is still doubling every couple of years. And the fiber does not have an infinite bandwidth. There's a few things we can do yet to gain another factor of 2 or maybe even factor of 4. But think about it, a factor of 4 gains you 4 years. Hey, what are we going to do after that? Well, it's not the end of the world as we know it. But what it does mean is you start to have to put in double the number of fibers every 2 years. And nice if you're in the fiber business, but is that very practical? So a lot of us are starting to think about, let's go back to the early days when we were all looking at chunks of physics and wondering whether it worked, and saying, it's time for another chunk of physics. Now, what might that chunk of physics be that will change everything again?
Using the laser in our day-to-day lives, whether we are aware of its presence or not, is a huge part of the laser's success. Maybe just as important is the laser's ability to be used for so many different avenues of research that may one day lead to concrete applications or understanding of our planet and even those beyond.
When a star is not bright enough to have enough light that you can split it off and look at the wavefront while still trying to see what the star looks like, you don't have enough light to do that, we can produce an artificial star up in the atmosphere. The concepts are shining a laser up into the lower part of the atmosphere at about 10 to 20 kilometers and getting some Rayleigh backscatter or molecular backscatter. Just like you shine your headlights into the fog, you can get backscatter light. Another more efficient way to do it is to shine a sodium laser, an orange laser, up into the sodium atomic layer at about 90 kilometers, very high in the sky, well above the disturbing atmosphere, and it produces an artificial star that we can use for wavefront sensing. That allows us to look anywhere in the sky without having to have a bright natural source nearby.
I think that at the most fundamental level, what research does for the country is to provide a means of exploration, a means of addressing the unknown in ways that, on the one hand, merely satisfy intellectual curiosity, but on the other hand, address some of the most fundamental questions that we have in our own lives and careers. In physics, what's the nature of time?
The way to make real advances is to explore. We don't understand nature. Okay, we really need to get better understanding of nature. But bigger than that, there should be some research on things that may not even have foreseeable application, or the application is beyond what we can even envision.
Anytime you can put matter under extreme conditions, you're going to learn something. Okay, and these lasers give us the capability to go places that we've never been before. I already mentioned the applications where we can access parametric regions that we used to be able to reach only by underground nuclear testing, for example. So that'll tell us things about the planetary interiors, such as, the Jovian interior, the accretion problem, astrophysical jets, a number of things that are intensely being investigated.
I don't envision lasers coming more into society and solving those big problems. What I do envision is lasers being critical to figuring out the science that's going to let us get solutions to those problems.
Of course, new products, new developments, new procedures have been the basis of our economy at least since for the last century. Will obviously continue to be so, perhaps most prominently in the field of energy and health, and we can't get to the future from where we are without the continuing input of basic research to guide that process.
Basic research is vital, and I think that is an issue for us as a nation to address. If you look at the laser in particular and the work done, say, at Bell Labs, where some really fundamental research was done years ago, that we effectively take for granted today, especially you look in the telecom market, and lasers are critical for the bandwidth that we all use today. And the challenging thing with basic research is no one could have predicted where that work would have gone back then. yet the benefits are profound for all of us. And I think we've lost sight of that a bit. And obviously budgets are tight, et cetera. But I do think that basic research is vital for the nation. And indeed, lasers are sort of a poster child for a lot of that work. And we're certainly thankful for it.
Right now, it is no stretch of the imagination to believe that there are tens of thousands of different research projects being conducted utilizing the laser. Perhaps the biggest of these in size and potential is the use of lasers to produce energy.
Well, if you go back to the first ideas of laser fusion, which actually were generated just 3 days after Ted Maiman's demonstration of the laser itself, just a few miles away at the Lawrence Livermore lab in California. A guy there called John Knuckles came up with the idea of using the laser's ability to concentrate energy in time and space to compress fusion fuel. And then a few years later, in 1972, he published his ideas in Nature and predicted that a laser of about a kilojoule in scale would be needed to make this work. Now, I have a kilojoule laser in my lab, and I can tell you that it's not enough. And so it turns out that what went wrong in those early assumptions was a lack of understanding or lack of appreciation, perhaps, of some of the instabilities that are inherent in a high-power laser interacting with matter. You can both drive plasma waves, electron waves and ion waves oscillating through the plasma, and you can drive hydrodynamic turbulence in the system. And both of those constrain the problem to a very small region of phase space. And it means that rather than using a kilojoule laser focused down to an incredibly tight spot, you need a much bigger laser, 1,000 times bigger laser, a megajoule laser, focused down to much more relaxed conditions and assemble the fuel using that much larger system. And it's taken 30 years or so to develop the laser technology to get from the few joule to the kilojoule to the megajoule level, which is now, as I say, culminated in this national ignition facility. So, and we shall see whether it works or not, but there is high confidence based on the first year's worth of experiments that we're on track for the next year or two.
With the building of the NIF Laser and its dedication recently, we will finally have a laser big enough to find out if these ideas that we've been working on for the last 30 years are real or not. And so I just, hope to see that they can actually ignite one of those pellets before I die, because I spent my entire professional career building the base to the point where we could do the experiments we're about to do.
Conceptually, think of it like a car engine. So you have a piston that compresses some fuel. In our case, the fuel is a small ball-bearing sized solid pellet of hydrogen isotopes. They're tritium and deuterium isotopes of hydrogen, which contain respectively 2 and 1 neutrons in the nucleus. The piston compresses that small ball-bearing sized pellet of fuel on top of itself at a scale that, to compare it with, it'd be like compressing a basketball down to the size of a pea. But because you already start off at about 1 millimeter or 2 in diameter, you're compressing it down to a few tens of microns, smaller than the width of a human hair. And if you can do that, and if you can do that in a controlled enough way, you can get extremely high densities, typically 1,000 grams per cc, so that's 100 times the density of lead. And again, if you do it right, you can get very high temperatures, typically 10 million degrees. If you can achieve those conditions, then the atoms will overcome their coulombic repulsion, they'll combine together, and those hydrogen isotopes will form helium, which is an inert gas, and a neutron. The neutron escapes and is used to do nothing more than heat up a blanket which boils water to drive a steam turbine.
Once ignition's demonstrated, I think there'll be a technological revolution that will make facilities that are smaller than NIF, but equally capable of producing energy, because we're going to learn a lot, if you look, NIF has a lot of margin in it, at least we believe it does scientifically.
The HYPER project is there to try to build on the work going on at the National Ignition Facility in the US, but convert it from a scientific proof of principle into a commercial engineering reality. This is a consortium of scientists from 10 different countries who have come together, and their goal is to try to realize a long-term dream. Can you use a high-power laser to initiate fusion at a level that's sustainable to deliver gigawatt scale electricity to the grid.
When ignition works, you're also going to see a huge interest in making fusion a reality, well before the time scale envisioned by the proponents of ITER. Okay. And I think a number of things that will happen after that to make it happen. I think we'll see efficient diode pumping, where solid-state lasers may be a driver of choice for energy applications. For energy, what matters is the driver efficiency, the wall plug efficiency, times the gain of the system, where gain is defined as the energy out versus the laser energy in, has to be a number of the order of 10. And so if we have a 10% efficient laser, a gain of 100 will make it work. Once we get ignition and burn, there's just going to be great uses for these neutrons. So I think you're going to see an energy revolution where the joke about fusion has been it's an energy source of the future, and it always will be. Yeah, and I think that's going to change when people say, yes, we have it in the laboratory now. It's not an imagine what, it's imagine when.
With so many uses already discovered, the idea that the laser was a solution looking for a problem is laughable today. But even 50 years after Ted Maiman's Ruby laser was first fired, the laser field is growing, and the next 50 years promise to make an even bigger mockery of that famous phrase.
Well, that's the nature of science, People keep contributing, and the science grows, and a lot of people add new ideas and so on, and so lasers have gone that way.
Of course, the term enabling technology is way overused, but it is true for the laser, definitely, that it is an enabling technology. And what I find fascinating is the prospect that the laser not only is used when no other technology can achieve what it can achieve, but where we as in not only the photonics industry, but the manufacturing industry, from my perspective, finally acknowledge that the laser is a wonderful tool to substitute a lot of other tools that we're using today. And if and when the industry will leverage this inherent ability of the laser, I think that we can grow vastly for a long time to come. I, in my mind, still think that we're at a very early stage of development in the laser industry, and there are many good years to come.
This is a field that is just set to expand enormously over the next 10 years, next 20 years, next 30 years, throughout this century. I mean, just think of the applications in which lasers and photonics are being used already, and you look at the rate of growth and penetration into different fields of science and different areas of society, and that's an incredibly steep curve that is only set to continue to increase. So if somebody wanted to work on a technology that underpins many of the applications that will transform our society over the next few decades, this is the field to be in. High power lasers, photonics, use of advanced optics and so forth. I've no doubt it will continue to transform communications, continue to transform high-speed computing. I hope and believe that it will transform our search for abundant clean energy. I think there's a good chance that it will transform many of the medical and pharmaceutical applications. The list is endless. This is a great field to be in.
The first dye laser system that we built and actually were testing on human beings managed to catch fire in the clinic, and the nurses and patients were running down the hall attempting to get away from this thing. And I was thinking at the time as a medical student, there goes my career, because I was just a student at the time. But in fact, the powers that be were very kind, and the head of the clinic, Ken Arndt, was a laser aficionado from the 70s himself, really one of the pioneers in this field, forgave me these sins, and it turned out okay. Later, the FDA approved the device. It's still the gold standard for treating these kids, but I will never forget the fact that lasers can be the dark side of lasers. They can crash and burn, quite literally.